going to be walking through the simulation part A for this virtual lab. In this lab, what you're going to be looking at is different kinds of waves. You're going to be focusing on the properties of waves like amplitude and frequency and wavelength. Normally, in our normal class, we'd be able to take these things outside, big long strings, and start actually making our own waves. But I found a simulation that's pretty close to what we would normally do in class. So I'm going to walk you through the first part of it, because this first part really builds a good understanding of what we're doing, and I want you to be able to actually find these things, and then you'll be able to work through an experiment a little bit more. I'm going to not give you all the answers here, but I'm going to kind of walk you through the thinking here, and then I'll allow you to kind of fill in the blanks for yourself, and then we get down to simulation B for the waves intro. I'll show you what that looks like, let you kind of mess around with it, and then see what answers you guys get. So to start off with, we're going to open that document. We got our PhET simulation. There we go. So what we're going to be doing is we're going to be creating a wave along this string or this medium. So your setup should have oscillator, no end, slow motion, and no dampening. Okay. Yours is probably already propagating, making waves, and that's fine. Okay, I'm going to start mine right now, and we're going to see the generation of a wave. Now, this generation of a wave, if we were going to do this in class, would be much harder to do because it would be pretty active and be kind of difficult to slow it down and actually see each wave, crest and peak. I have lots of animations, as you can see from my PowerPoint slides, that shows this in slow motion and shows each of these little pieces and particles of the string. So our first question is talking about some of the difference between transverse and longitudinal waves. Now, when you're reading this week, we talked about transverse and longitudinal waves and the difference between them and how you would know that. So this question could be kind of difficult. A lot of our issues with these words, transverse and longitudinal. A longitudinal wave, it's not like a normal wave that kind of propagates through. Okay, it's more like a sound wave or a shock wave. Okay, so this question and number two kind of get into the same idea. Okay, a transverse wave is when the disturbance and the propagation of a wave are perpendicular. So if you look, this oscillation is going up and down, but the wave is traveling along the string in the X direction when the disturbance is in the Y. Okay, so that's something that will pop up. Those are two pretty in-depth, kind of big idea vocabulary words, transverse versus longitudinal. Now go back and look at my slides, okay, for this class. There's some really good animations to show the difference between a transverse wave and longitudinal wave. Transverse wave, I'm pretty sure I show like a water wave, like waves on the beach. And then longitudinal, it's more like a speaker. Okay? The speaker is pulsing and the waves are propagating out away from it. Okay, so how do you know? To get you started, we're looking at where the disturbance is and how the wave propagates from it. Same thing with number two. In which direction is the wave traveling compared to the disturbance? Perpendicular or parallel? Well, depending on if you chose this was transverse or longitudinal. If it's transverse, we would be talking about a perpendicular type of wave disturbance. Here's our disturbance, here's our wave, perpendicular. Okay, so now it says to spend a few minutes increasing and decreasing the amplitude. Okay, so in our simulation, we've got our little amplitude right here. I want you to mess with it. Okay, I want you to slide it around. I'm sure you're just going to slide it all over the place, and oh, look, it's done some stuff that's kind of difficult to tell what's going on. And because it's not attached, there's no end, it eventually will go away and we'll go back to normal. So if you notice, if you do this really fast and sporadic, you get all kinds of weird stuff. It almost looks like it's glitching, but that's not really what we want. Okay, so you can mess with it for a second, but I'm actually going to start at a low amplitude, something that we can actually see, a low amplitude right there. Okay, about 0.2, 0.3, something like that. And you can see I have this little tiny wave, right? Be like barely moving up and down a string. And as I increase that, my string is moving higher and lower. And as I keep going, it's going higher and lower and higher and lower and higher. And as we keep going way up, we get these really, really steep looking waves. Okay. So what I want you to do, I want you to describe in your own words your definition of amplitude. Now I know there's a definition in the book, or the book chapter that I've had up. I know there's a definition I gave you, okay, in my notes, but I want you to use your own words. I want you to tell me what it means to you, okay? So it'll help you kind of write down what you know of as you've been messing with this simulation. That's kind of the important piece, okay? So once you've described that, you can pause the video at any time so you can work through this with me. Now we're going to explore how amplitude affects wavelength. Okay, so it says, use the following settings and measure the approximate wavelength. Pause the simulation after a few waves, measure and use the ruler. Grab the ruler and drag it to measure. So what we're going to do, we're going to take our amplitude and our frequency. I'm going to pause, restart. We're going to set our amplitude to 0.75, and you can drop it down to 0.75. And our first frequency is going to be 1.6 hertz. We're close. Okay. So we got amplitude, we've got our frequency, and now we're going to measure the wavelength. So what we're going to have to do, slow motion, it tells us that we're going to have to use a ruler to measure it. So let's propagate some waves here. Right there. Perfect. There's a couple ways you can measure a wavelength. Again, go back, look at the reading, look at my PowerPoints. A wavelength you can measure from the crest of the wave to the crest of the wave. Okay, so crest to crest. We can measure it from trough to trough, so the bottom of the wave. If you aren't familiar with these vocabulary terms, crest means the peak or the top, and trough means the bottom. Or we can measure from the zero through a zero and through to the next zero. Now the reason this is a little bit different, okay, is if we go through from one zero to another, we haven't gotten a full wave, right? We've only gotten the top part of a wave. A wave has basically a maximum, a top, and then a minimum, a bottom, before it's propagated one full wave. So we need both, the top and the bottom, the crest and the trough, to make a full wave. So if we do that, this is approximate. I'm going to do it from this zero, because I got it pretty good, to here. We're going from 0 centimeters out to about 3.9 centimeters. I'm not going to be looking at how accurate you are. Let's just do that, 3.9 centimeters, because we have our sig figs here. We've got 2 significant figures in this number. It looks like we could be good up to 2 significant figures here. So let's do that. It's about 3.9. This is about the 8, right in between. Sounds good. If you've got 4, that's fine. You can also check 1 to about 4.9. 4.9 minus 1 is about 3.9. Now we'll do this for one more, and then you guys can do the rest. We'll go 0.9, 0.9 amplitude. And what's the next one? 0.6. Okay, so we'll restart. We've got our ruler. Hit the go. I'm going to try to stop it again. This time I'm going to stop it in a different spot, and we'll measure a little bit differently. There we go. You can measure it crest to crest. This is a new amplitude. So if we measure this, we go from 0. Again, it's about 3.8, 3.9. Okay. We'll say about 3.8, 3.9 again. Yeah. Do that again. 3.9 centimeters. Okay. So I'll let you do the rest of these. All right, we'll keep moving on. So when amplitude increases, we're looking at a difference in wavelength. What happens to the wavelength? Okay, so I'll let you finish working through this, and I want you to think about, once you pick the correct answer here, okay, when amplitude increases wavelength blank, I want you to think about why that would be, okay, based on your description of what amplitude is. Okay, you don't have to write anything about that. I just want you to think about it. I want you to think about what that means. Okay. 6 is, this means the relationship between amplitude and wavelength is blank. And you can work through that one too. And then when amplitude increases, energy blank. Now we talked about energy a while ago. Okay. And in our book chapter and in the PowerPoint slides, energy is mentioned, but I want you to think about how the energy in this system is changing as you change the amplitude. Okay. Think about why. Again, always think about why. All right. You can pause the video as you go. So number 8 says return the amplitude to 0.75 centimeters. So let's do that. Go back down to 0.75. Okay. Then spend a few minutes exploring the frequency of the wave by increasing and or decreasing it. So we're going to take our ruler away so we can see, and we're going to mess with, let's restart. We're going to mess with the frequency. Again, you go crazy with it, it makes something that looks really weird, right? Doesn't quite look like a wave. So we're going to start at one point, okay, pretty far down, and we'll start increasing it as we go. Wow, that one, pretty low frequency. And as we go up a little bit, there's a little bit higher frequency. Okay. And you can mess with this as you go too, right? So as we get higher in frequency, see some changes happening in this wave. Okay. All right. So after you mess with this a little bit, it says to describe frequency in your own words. Ooh, there we go. It says describe frequency in your own words. Same thing, okay? As you increase this frequency, or you go from high frequency to low, I want you to think about it in your own words, not looking at the book, not looking at my PowerPoint slides. What is frequency? Okay? You can use this as a guide, but I want it in your own words. Okay. I'll give you some time to think about that. Increase the frequency. Seeing a couple more waves on the screen as we go up. Let's see. There we go. Even more waves on the screen. So what does that mean? All right. The next one says we're going to explore how frequency affects wavelength. So if you notice on the last one, all the frequencies were the same and all the amplitudes were changing. So we picked one variable to change the amplitude, and we kept frequency constant to see how that affected wavelength. Now we're doing the same thing. We're going to be affecting the frequency while keeping the amplitude constant. Okay, and that's going to give us the relationship between frequency and wavelength. So what we're going to do, I'm going to pause again, restart, and we're going to set our amplitude to 0.75 and our frequency to 1.4. 0.75, 1.4. Okay, there we go. And I'm only going to do the first one for you. Okay. So once we get to these, we pause the simulation after a few waves so we can do the ruler. We're going to try the same. I'm going to do the same kind of thing I did before. I'm going to measure it, try to stop it at 0 and take a measurement, try to stop it at the peak and take a measurement. So there's our rulers, and we're going to start. Okay, we'll get a wave or two on. We've got our 0 here. Okay, we go through 1, 0 onto another, and we have our measurement. So our measurement here is going to be, I would say, about 4.5, right, between 4.4 and 4.6. It's about 4.5. So we'll type that in. And that's centimeters again. Okay. And you can do the rest of this one, okay? Just make the adjustment of the frequency, restart each time, and then if you don't quite get it right, you can move these around and get your wavelengths. So once we got our wavelengths, they're all in centimeters, same thing as before, they were in centimeters. I want you to look at the relationship, okay? Frequency is increasing. What happened to your wavelengths? Did they go up? Did they go down? What does that mean? So as frequency increased, as we increase it, what's happening to your wavelength? And the number 11 means that the relationship between frequency and wavelength is blank. Now, I didn't cover this on the last time, okay, because we've covered this before in this class, what direct and inverse means. We've done it a lot. Just to refresh, direct means that as one increases, the other increases. Inverse means as one increases, the other decreases. So they're opposite of each other, okay? And not related would mean as one changes, the other one doesn't. It stays the same. Okay. For number 12, it says return the frequency to 1.5 hertz and the amplitude to 0.75 centimeters. So 1.5 hertz. Make those adjustments, and then 0.75 centimeters. Okay. Get those rulers out of the way. Now focus your eye on one bead of the string. Slow motion will help. So I'm going to keep it on slow motion, okay? And we're going to focus on this green bead, okay? This green one. You can focus on any one. I'm going to focus on this one. I'm going to keep my mouse kind of right here where it is. All right. Now, as you're going through this, I'm hoping that you notice that the green bead isn't moving across the x-axis, right? It's just going up and down. It's not actually moving in the x direction. And you can see that in a lot of the PowerPoint animations that I have. There's quite a good animation where I zero in on one particle and its motion in the wave, okay? But this is helpful too. So this is going to be along with that PowerPoint. Now, I want you in your own words again to describe the motion of that bead, okay? In your own words, what's happening to that green bead as the wave propagates through the string? Number 13, through the same evidence that we just saw here, right? Looking at this green bead and how it's traveling and how it's moving. Number 13 is asking, do waves transfer matter? And it wants you to use evidence from the simulation to support your answer. And this is why throughout the whole process I'm having you think about your answers, okay? So, from what I can see right here, this green bead is not moving down the string, right? This particle, this little green bead, it's just moving up and down. So I would say that waves do not transfer matter, right? Because this piece of matter is not transferring down this wave, right? And the evidence I would be using, the evidence would have to be from the simulation. Okay, so I'm seeing that this green bead is not changing position in the x, and that would be my evidence. All right. Just kind of give you that one, but I want it in your own words, okay? I want you to tell me what you see with this green bead, what you're actually seeing in your own words. And then last piece for today before I open up the intro, it says to draw a transverse wave. And label the crest, trough, amplitude, and the wavelength on here, okay? Now, you should be okay to do this after doing the simulation, and you should have a good idea of where the amplitude is, the frequency, and then how to measure the wavelength can show you the wavelength as well. If you have a problem with this or you aren't sure where these labels should go, okay, rewind this video because I do talk about crest and trough and where those things are, or go into the PowerPoint slides that are available to you and check out where all of these things are, okay? I just want you to be able to draw where this is. And this line right here is representing the dotted